guys, this next video is going to be on measurement and significant figures. So we say that every measurement has some degree of uncertainty associated with it. This is going to depend on the precision of the measurement. And this is ultimately dictated by the instrument. You can imagine that a $5 graduated cylinder probably doesn't measure volume as well as, say, a $50 graduated cylinder. Okay? A measurement's uncertainty is expressed by the number of significant figures. And this is the number of certain digits and one uncertain digit. So in this class, unlike maybe some of your previous science classes, the way that we record data and the way that we perform measurements really matters. Okay, both in terms of that initial record keeping and also then in terms of our kind of data analysis. So I guess I'm going to pose a question to you guys first, and that would be in examination of this nail and the piece of equipment given. Okay, so we're given a ruler here with gradations that are to the ones place. I'm asking you the length of this nail. Okay, we can clearly see that this nail is somewhere between the 3 and the 4, on the right side of 3.5 likely. And so I think it's pretty reasonable to estimate maybe 3.8. And the idea here is that we are certainly sure about the 3, right? It's in between 3 and the 4. We can't argue that. But this 8 is a guess. And so we call this an uncertain digit. And so this whole measurement, 3.8 centimeters, is to say that we have 2 significant figures, okay? And it's weird because, if we're evaluating the exact same nail, we might actually come up with a different answer. Okay, so now all of a sudden, if we have the following ruler where the gradations are a little bit different, where we're actually given values in the tenths place, we can then actually begin to see that, okay, it's up over 3.9 centimeters. And maybe reasonably we can estimate that it's, say, 3.94. So the idea here is that we have 2 certain digits, this single uncertain digit, and so we arrive at 3 significant figures in our measurement. And this is kind of our overarching defining statement here, is that in this course, we are going to record measurements to one more place than the gradations on the instrument, okay? All right, moving on. We're next going to take a look at, if we are given some value, okay? Can we talk about the number of significant figures that are present? So we have rules for counting significant figures, and 3 of the 4 rules that we're going to take a look at deal with zeros, as it were. This first kind of indirectly does, I suppose. We're going to say that non-zero numbers can be counted as significant. So within 537, we have 3 significant figures. In 782.3, we have 4 significant figures. Okay. The next thing we're going to take a look at zeros that appear outside of our number, okay, kind of like at the beginning of our number. And we're going to say that these leading zeros are never counted. The idea is that this number here really only has the significant 2 and 5, because just as easily we could take 0.0025 and express it using scientific notation. And in doing so, those zeros drop away and we're really just left with 2 meaningful digits. Likewise, we see this, whether we have the 0 out front of the decimal or not. In this 0.043, we still have 2 significant figures because we can express the 0.043 as 4.3 times 10 to the negative second. Besides leading zeros, we can also talk about captive zeros, or what we may call inclusive zeros. And these always count, okay? So here we see the 0 wedged in between the 1 and the 8. So we're looking at 4 significant figures. Over here, this 50,347, this is going to count, giving us a total of 5 significant figures there. In this last case here, rather than talking about, say, leading or captive zeros, we're lastly going to talk about trailing zeros. And these count only if there's a decimal place. So in this case, we find that with 100, because we don't have a decimal place, the only thing that really matters is 1, okay? This is a suggestion that probably this is an estimation, right? This is going to be an uncertain digit, and these, we're really not even close to estimating. And we're going to see a good example here in a second that reinforces the usage of a decimal point. Here, if we're taking a look at this value 4.20, this, maybe we're measuring, say, the volume, and we're taking a look at a meniscus. And on the burette that we're using, maybe we have markings of 4.1, 4.2, 4.3, and it's right exactly at 4.2. And because we're given tenths on this piece of instrument, or on this instrument rather, we can reasonably estimate to the hundredths. Okay. Here we have a decimal, so this one differs than the first example there. So we have 3 significant figures. Probably again these 2 certain, and this one maybe uncertain, but valuable nonetheless. In this last case, we again have 3 significant figures, 1.00 times 10 to the negative 4th. It's that decimal point that really kind of firms these up as the certain digits, and this one is our uncertain there. Okay, that last is 0. All right, moving on. We're going to get back to this idea of kind of when the decimal truly matters and when it doesn't. So again, imagine we're trying to find, say, the weight of an object. Okay, and so we're given the following scale. Well, in this case, because I'm only given thousands, gradations, it's really only reasonable to estimate to the 100th place. Okay, so this in itself, it is an uncertainty, right? So we estimate the 5. The zeros are kind of meaningless, so we only have 1 significant figure there. But if we're evaluating, again, the exact same object, and all of a sudden we just have, a different scale that we're working with, or a different balance, because we are given now tenths place, right? We can estimate, or tens, places to the tens, we can estimate to the ones. And with that in mind, this is pretty much right at 500. It's not 501, it's not 499, or it looks to be the case. So this decimal really kind of reaffirms that again, we are sure about the 5 and the 0, and this 1 is a pretty, or the 0 rather at the end here is a pretty good estimation. Okay, so again, going back to the idea that the number of gradations is going to dictate the certainty in our measurement. In this case, we have 3 significant figures. Okay. Now, having pieces of data is great, but ultimately in this class, we're going to be doing a fair amount of calculations. So we have to figure out how we can manipulate data that has some number of significant figures to figure out, how precise our final answers can actually be. So before we get there, just a quick aside, concerning 2 different things. One, numbers that we obtain by counting, and the second would be conversion factors. So here we say that exact numbers have no uncertainty, as they're obtained by measurement, and therefore have an infinite number of significant figures. If somehow we were to isolate 170 atoms, 170 would not limit us as far as our calculations go, and we'll see that here in a moment. Same with 32 trials. If we were trying to find the rate of a reaction over the course of 32 trials, we were doing averages, 32 would not limit us, okay? So again, it's a number obtained by counting. Likewise, if we're going to talk about, conversion, say between inches and centimeters, a conversion factor isn't going to limit us. And we're going to say that conversion factors have some infinite number of significant figures. Okay? So let's get to measurements. In this class, we're largely going to be manipulating data and significant figures in terms of multiplication and division. Okay, and these have 2 different kind of distinct rules. And the reason we care about these rules is because our calculations cannot be more precise than our instruments. If we are, say, calculating the density, right, and we have some mass and we have some volume, it'd be kind of unreasonable to say that the density of an object is like 4.279371345 grams per milliliter, if our measurements in the first place was only like 3.2 grams and 9 millimeters, right, or milliliters rather. So our final calculations cannot be more precise than measurements. When it comes to multiplication and division, the number of significant figures in our final answer is going to be the same, or kind of limited, by the number with the least number of significant figures. So in this case here, we might take 4.56 and multiply by 1.4 with 3 and 2 significant digits respectively, and our calculator may shoot out that answer. In honors chemistry, great. Slap it down on the page, let's move on. Okay, but in this class, again, you're essentially communicating how good your data is, right? And so this rounding matters. And so because we are limited by the 1.4 as having 2 significant figures, our final answer can only have 2 significant figures. So we have to limit ourselves to the tens place. 6.38, we will round up to the 6.4, okay? When it comes to addition and subtraction, the rule differs a little bit, okay? Or I guess I should say a lot of it. What we really care about is the number of digits after the decimal place, okay? So the answer will have the same number of decimal places as the number with the fewest places to the right of the decimal. So here, 12.11 plus 18.0 plus 1.013. Again, our calculator shoots out this answer. But in taking a look at these terms, we only have 2 digits after this decimal. We got 1 after this decimal, and we got 3 over here. So it's this 18.0 that's going to limit us, which is to say our final answer can only have 1 digit after the decimal. Okay, so we arrive at 31.1, and we round this down to just the 31.1 here. Okay. So a quick question, just kind of reinforcing this. Let's say I'm asking you to convert, say 1.1274 atmospheres, okay, unit of pressure there, to torr. And I give you this conversion factor. And so the question is, what is this going to be in torr? All right, so I've set up a quick proportion. 760 torr is equivalent to 1 atmosphere. This equals some amount of torr we're trying to solve for. Can have the same units across our numerator, same units down in our denominator. I'm going to solve for this. The question is, which of these answers is appropriate? Okay. And so what I'm hoping is that you come to the conclusion that this is a conversion factor. So it's really not going to limit us. So what we are going to be is truly limited by the number of significant figures total that this number has, right? This is a multiplication step. So the number we're looking at here is 5. And so neither of these answers are correct, right? This would attempt to throw you off if we're thinking that we're limited by the 760 here. This would throw you off if you merely record the number your calculator shoots out. We're gonna have to take this and we're gonna have to make sure that it just has 5 significant figures. So we're looking at 856.82 torr as our final answer. Thanks, guys.